Hi and welcome. This video is part of a series of videos on solving the wave, heat and Laplace equations. This video specifically focuses on some of the harder examples of the wave equation, so if you haven't solved a wave equation before, I recommend first viewing the earlier videos in this playlist, and I'll put a link on the screen for this right now. Otherwise, let's get into it. So for example 1, you'll notice up here that these are our boundary conditions that are homogeneous, and these two down here are our initial conditions, and one of them is non-homogeneous, this second term here. You'll see that this non-homogeneous term is made up of two separate terms that are added together here. So the first thing you're going to want to do is step 1 is notice that the wave equation, so u of tt equals c squared u of xx, is linear and homogeneous. Now this is important because if it's linear and homogeneous, we can use the superposition principle. Now, if you recall back, the superposition principle is where we have a solution u, which is equal to two independent solutions, which is, in this case, it's going to be u of 2 plus u of 7. And you'll see why that is in a moment. So just note that so that's really important that you write that first part. So step 2 would just be find u of 2 and u of 7 using u of n. So we actually already found u of n in an earlier video, so you can go back and re-watch that video, and I can that link was up earlier in the at the beginning of this video. But if you recall back, and you should be able to find u of n anyway if you're watching this, so u of n equal to b of n sine n pi over L x sine pi n c t over L for n equals 1, 2, so on. So that's our u of n. Now you'll notice, and so this, our u of n, already encapsulates the three homogeneous conditions. Now what we're just focusing on is that last non-homogeneous condition. So you'll notice that this is a derivative here, so we're going to need to take the derivative of u of n with respect to t. So u of n of t, oops, it's not very neat. U of n of t is just going to equal b of n pi n c over L sine pi n x over L cosine pi n c t over L. Now for our non-homogeneous condition up here, you'll see that it is for t equal to 0. So we'll just take that now, fill in at x 0. So you'll notice that if we put in t equals 0, then that whole cosine is just going to go to 1. So we're going to just end up with b of n pi n c over L sine pi n x over L. So now we've got this here, and you'll notice that that is equal to what we've got up here. We can set both of those sides equal to each other. Now what we're going to do, because we're using the superposition principle, we're just going to take the first term here. So we're going to set 3 sine 2 pi x over L. We're going to set that equal to this side over here, b of n pi n c over L sine pi n x over L. And now all we want to do is match n, so we want to find n and we want to find b of n. Now n's pretty easy to find. If we're just matching the left hand side with the right hand side, you'll see that n here should equal 2 in order to match this. So we know that n should be 2, and that's why I wrote up here u of 2, because I could already see that. So n equals 2, and then to find our b of n, we just solve for b of n, so it's pretty straightforward. If we divide by the sine function, we're just going to end up with 3 equals b of n pi n c over L, but here we've already said that n is 2, so I'll just write pi 2. So that is going to leave us with a b of n that is equal to 3L over 2 pi c. So writing this all together as our solution for u of 2, it's going to, and we're using this u of n up here, using this one here. We're just filling in what our b of n is and our n. So our u of 2 is going to equal 3L over 2 pi c sine 2 pi x over L sine 2 pi ct over L. So that's one of those solutions. And now we're just going to find u of 7. And again, we know it's u of 7 because we know that n will have to equal 7, because if we now set this side here, this term here, equal to, I'll just write this down first, pi sine, we have pi sine 7 pi x over L should be equal to the same as what it was up here. We're just doing the same thing essentially twice. Pi n c over L sine pi n x over L. You'll see n should equal 7 here, and then if we solve for our b of n, if we divide both sides by the sine function, that just goes to 1, so we end up with pi equals b of n pi n c over L. And then solving for b of n, we just end up with L over 7c. So we can write out in full what our u of 7 equals, and that equals L over 7c sine 7 pi x over L sine 7 pi ct over L. So you'll notice that we're leaving the t's and the x's as they are, and we're just filling in what the b of n and the 7 is up using our whole u of n function up here. So now we have u of 7 and u of 2, we can do step 3, which is simply u equals u of 2 plus u of 7. So we can write that out. U equals, I'll just copy this, u of 2, and copy, paste, and whoops, plus, and then we'll just paste the u of 7 down here. Copy, paste. Yeah, so this is our specific solution here. I'll just write it in here. specific solution. So this solution here fulfills all of the boundary conditions and initial conditions, all of these up here. So hopefully that makes it clear. The only real, it's very similar to just solving the wave equation with one non-homogeneous term, whereas like if we didn't have this, you do the same thing really, but you just make sure you invoke the superposition principle, and that allows you to take two separate terms that are independent and just find solutions to each of them and add it together at the end. Now, example 2 is a little bit trickier than example 1, but it's still not too bad. You'll see that we have two non-homogeneous initial conditions, these being our initial conditions, these up here being our boundary conditions. So going through the process of separation of variables, you should be able to find that your x of n equals sine n pi x over L, and that the t of n is just going to stay in its most general form possible because we don't have any homogeneous conditions. So a of n cosine c n pi t over L plus b of n sine c n pi t over L, where a n and b n are some constants. You should write that, but I'm saving time here. So our u of n together is going to look like this: sine n pi x over L, a of n cosine c n pi t over L plus b of n sine c n pi t over L for n equals 1, 2, etc. So this is our sort of general form here. What we want to do is this right here obeys our two boundary conditions, but it doesn't yet obey those two initial conditions that we've got. So step 1 would just be find u of n. Step 2, we need to find two solutions really, because we can see that one solution itself isn't going to satisfy both of those initial conditions. So we essentially need to find a u1, so our first solution, which satisfies, maybe I'll write that in green, so u1, which satisfies u of x naught equaling minus 4 sine 5 pi x over L, and it also needs to satisfy u of t x naught equals 0. And then we need to find a second solution, where u of x naught equals 0 this time, and u of t x naught equals sine 2 pi x over L. So it needs to satisfy those two conditions there. So you'll see all I'm doing is satisfying this first condition here while the other condition is set equal to 0, and then in the next solution I'm finding something that solves this condition while the first condition is equal to 0. And then what we can do after that, once we've found u1 and u2, is we can just use the superposition principle and sum them together. And we can use the superposition principle because the wave equation is linear and homogeneous. So let's find u1 and u2. So I might just put a box around this. let's find u1. So for u1, we need a u of x naught equal to minus 4 sine 5 pi x over L. And that should be equal to, so from this, we'll go back to this u of n. And if we put in t equals 0 from here, if we put in t equals 0 to our u of n equation up here, you'll see that we're just left with a of n sine n pi x over L. Because this, the cosine up here is going to go to 1, and this one here is going to vanish and go to 0. So essentially all we need to do now is equate terms, so match the left-hand side with the right-hand side. So you'll see here that we need to find a of n, b of n, and n. So you'll see that a of n here should equal minus 4, because we're matching this with this, and you'll see that n should equal 5, because that here needs to match this here. So n will equal 5, and our b of n will just equal 0, because that's not even in here. So we can write the solution as u1 equals to minus 4 sine 5 pi x over L times cosine 5c pi t over L. And you can see that we get this from this u of n up here. So essentially we're just plugging a of n, n, and b of n into our u of n up here, and that's what we get. Now from here, we need to just also check that it satisfies that other condition, because remember up here we've done this and that's satisfied, but we don't know yet whether this part is satisfied. So let's just check that u of t x naught equals 0 is satisfied. So from our u of 1 here, if we put in t equals 0 into our u of 1 here, you'll see that the cosine is just going to go to 1. Oh, sorry, we just need to take the derivative of that first. Forgot about that, because that's a derivative here. So if we take the derivative of u of 1 with respect to t, we get u of 1 of t. And just doing that quickly, that's going to be 20 c pi over L sine 5 pi x over L sine 5c pi t over L. And then if we put in t equals 0, that whole term there, all of that, it will vanish and go to 0. So yes, that's satisfied. So now we need to find u2. Right, so for u2, we need the condition u of t x naught equals sine 2 pi x over L. So if we take the derivative of u of n with respect to t, we're going to get sine n pi x over L times minus an c n pi t over L sine c n pi t, that's not a t there, t over L plus b of n c n pi over L cosine Cn pi t over L. Right, so now if we put in x equals x and t equals 0, so u of n of t at x and 0, we're going to end up with our b of n c n pi over L sine n pi x over L. And we need this to equal sine 2 pi x over L, which is up here. We need it to equal this up here. So just equating coefficients, you'll see that, so we need, from here we need to find what b of n is and n and a of n. So b of n and n and a of n. You'll see here we don't even have an a of n, so we can let a of n equal 0. Our n here should equal 2 because we're matching that n with here, equating the left-hand side with the right-hand side. And our b of n, you will see that equating coefficients, we need b of n, c, n pi over L to equal 1 because that's a 1 in here, right? So solving for b of n, it just means that b of n equals L over 2c pi. Right, so now I'll just write this in up here, and then I'll just delete this messiness here. Right, and now we can write our u2, and that equals, so we're just using this u of n here, and we're just plugging in our n, a of n, and b of n, what we've just found here. So that's going to equal L over 2c pi sine 2 pi x over L sine 2 pi ct over L. Now again, just like the first example, the first u of 1 up there, we need to check that u of 2 satisfies. We had our other condition up here, so we need it to also satisfy this here. U x naught equals 0. U of x naught equals 0. And you'll see that if we plug in t equals 0 to u of 2 here, that whole thing will just vanish because of the sine function. So we can see automatically that that is satisfied. So because we've satisfied all our conditions, we can say, all right, step 3, can write by superposition principle, as wave equation is linear and homogeneous, therefore u equals u1 plus u2. So we can write u equals 2, and I might just copy u1 up here and copy, paste, and plus, and we can copy u2 here. And paste. And then that is the final solution here. So it's similar to the previous example, a little bit harder and a little bit more work, but really not too bad. Example 3 is actually really similar to example 2. So for that reason, I'm not going to go through step by step how to do it. You'll see that we have got two homogeneous boundary conditions and we've got two non-homogeneous initial conditions. You'll see that this initial condition over here is really similar to example 1, and having two non-homogeneous initial conditions is really similar to example 2. So all I'm going to do is show you that it's very similar to the previous example we just did, in that we use the superposition principle on 3 separate eigensolutions. So we're actually going to find 3 separate solutions that are independent of each other, and the first solution is going to satisfy these 2 conditions. The second condition, the second solution, sorry, is going to satisfy those 2 conditions, and the third is going to satisfy those 2 conditions. And then all you do by invoking the superposition principle is write u1 plus u2 plus u3 equals our specific solution. So hopefully all of that makes sense to you after watching example 2. So that's it for this video. Hopefully it's been helpful to you in some way, and if you don't enjoy doing maths, hopefully it hasn't been too tedious for you. If you do enjoy maths, hopefully you also found this fun. Let me know if there's something that I could improve upon and do better. Otherwise, I will see you in the following videos where we start on the heat equation.